Okay, it's going. Recap from last week. Quick recap from last week, just some basic terminology. Just shout it out for me. What's a proposition?
A proposition is a sentence that is either true or false.
And not both.
Not both.
No, not both. So that's a proposition. Do we remember what a predicate is?
Predicate is a sentence.
That could be, but isn't determined.
It's a proposition valued function.
Oh.
That's the best way to say it. It's something that if you fill in its variable, then it spits out proposition. X is greater than 2 is not a proposition. You cannot call that true or false. That's a predicate.
Right.
Once I plug in something for that x, now we can call it true or false. We can say that 5 greater than 2, we can call that true or false. Or 1 greater than 2, we can now call that true or false. This one is just a predicate. It's not a proposition, right? So one of the ways that we turned predicates into propositions is we plugged values in, right? We replace the variables with an actual value. That's one way that we can turn a predicate into a proposition. What's the other way that we can turn a predicate into a proposition? Add a quantifier. Notice that x greater than 2, true or false? You can't answer that. But if I say something like, there exists some number, some x, such that x is greater than 2, now you can call that true or false, right? Furthermore, if I replace this with for all, or for every, or for each number, for each x, it's greater than 2. That's false, but notice it's still a proposition. We're saying every x is greater than 2. Remember that? Mm-hmm. Are these quantifiers still a little weird for some of you? Should we go over some examples with them again? Or should we just move forward? You're good with the quantifiers? Everyone's good with the quantifiers?
Yeah.
All right. If you're all good with the quantifiers, we can keep moving forward. So after we talked about the quantifiers, what else did we talk about? Was that it? And then we just started doing examples of proofs?
Yeah.
Yeah?
I think so.
Okay. So now we started doing some examples of proofs. Let me close this for a second. And we're going to do some exercises. And the point of this is to try and get you comfortable with the notion of an axiom. And with only using your axioms, only using the assumptions that you get to use. So we're going to solve a bunch of problems, and we're only going to have these two axioms. These are the only two assumptions that we're going to make, and we're going to do a bunch of proofs, only using these two assumptions. Now, we're also going to use the fact that these are true. What's the difference between these two and these two?
Are those lemmas?
No. These two up here are consequences of logic. They have nothing to do with any field of mathematics. These two down here are only true in particular fields of mathematics. These two are just special cases of the one that we showed you. I showed you, we did a quick proof that if A circle B is defined and is equal to A, if A is equal to B, then A circle B for any operation where this is defined is equal to A circle C. So there's nothing to do with any mathematical operation.
You mean where C equals B? Yeah.
Oh, did I do the A to both sides?
Yeah.
If A equals B, then A circle C. I want to try and write it the same way I had it. I think that's the way I had it. So this was a proof we did. We didn't do this assuming anything about mathematics. We showed this just with logic. We did it using what we call logic with identity. So we had a basic notion of what identity means. Everything is identical with itself. A equals A. That's always true. That's a rule of logic. It's not a rule of math. Logic is at the foundations of math. Here's logic. Here's math. You can use, for any field of mathematics, you can always use logic. You can't use math in your logic. You can always use logic in your math. And it doesn't matter if you're talking about geometry. It doesn't matter if you're talking about algebra. It doesn't matter if you're talking about topology. It doesn't matter if you're talking about computation theory. It doesn't matter the field of mathematics you're talking about. You can always and forever use logic. These two down here, we only assume in algebra. These two up here, these are a consequence of logic. They're true everywhere, for any symbol that we put there. I did it specially for the plus and time symbol, because that's the case that we're going to use it in algebra. But for any symbol you put there, as long as it's defined, doesn't matter what that symbol is, as long as it's defined, this is true. So these two are not axioms. And for those of you doing the homework, who, I don't know if that's anyone now, you'll notice that when you're doing these problems, they don't list these two as assumptions for you. They only list these two. And that's why, because this is a consequence of logic. This is always the case. Now they're saying, let's assume that this is true. You never say, let's assume that logic is true. You're always using logic. You can't logic without logic. And we're always logicking about things in every field of study. Doesn't matter what the field is. From humanities to math to any field of science, anything. It's always just applying logic to that field. So in this class, we're just applying logic to mathematics. This is a consequence of logic. It has nothing to do with math. Here's what it means in two special cases. When you replace a circle with the plus symbol, it means this. When you replace a circle with the time symbol, it means this. That make sense? Am I overstressing that? All right. So that's why I call it L1, L2, meaning those are little theorems of logic. And then we have axiom 1, axiom 2. Now axiom 1 and axiom 2, these are just two assumptions that we're going to make, and we're going to prove things, only assuming these things to be true. So we'll assume that this is true, and we'll assume that this was true. Let's read through each of these to make sure that they make sense, because that could be dense notation the first few times you see it. So let's read what this top one says. This top line says, for every A, B, and C, if A is equal to B, then A plus C is equal to B plus C. Follow that? All right, read this next one for me.
If every A, B, and C, A equals B, then A times C equals B times C.
Yeah, you can always replace that with just implies if you're looking for a good English way to say it. A equal to B implies A times C is equal to B times C. Or if A equals B, then A times C equals B times C. Right? Okay, so those are the two that we get from logic. Now let's look at one of our actual assumptions that we're going to make. This one says for every A, B, and C, if A plus B is equal to A plus C, then B is equal to C. Notice it's kind of like the converse of that one. Right? And then, for every A, B, and C where A is not 0, then A times B is equal to A times C implies B equals C. Why do we say where A is not 0? Notice this. Is it true that 0 times 2 is equal to 0 times 3?
Mm-hmm.
Yeah. Does that imply that 2 is equal to 3? No. So 0 is a special case that doesn't make this work. Okay. So you feel like you understand what these four things are saying?
Yeah.
All right. So let's try a proof. Throw one up here, and then erase it. If x equals 5, 3x plus 4 equals 19. So I'm going to prove if x equals 5, then what was it? 3x plus 4 is equal to 19?
Yep.
Okay. General pattern for when you're doing proofs. You start with 1, and you typically start with let, and then your antecedent, the condition, the antecedent. The first part in an implication is called the antecedent. Use that language. This is the antecedent, this is the conclusion. If antecedent, then conclusion. So we're going to say let antecedent. Let x equal 5. Good? 2. Then 3x plus 4 is equal to what?
3.
Well, we know that x is equal to 5. Using just a rule of logic, everything's identical with itself. I can then substitute in 5 for x. That's just using logic. That's not a rule of math. So I know this is then 3 times 5 plus 4. Right? Now, it comes from definitions of numbers. We'll get into those later today, hopefully. But then 3 times 5, we already know what that is. What is it? 15. We'll show how to prove simple stuff like that, hopefully later today. Plus, 4 is still equal to 4. And then finally, 15 plus 4 is equal to 19. Notice that for this direction, we didn't have to use either of our axioms.
Right.
Good? Okay, now I think the next problem is to prove the converse of this. We're going to prove that if this, then this.
Okay.
Yeah.
So 3x plus 4 equals 19. You remember that. So we have if 3x plus 4 is equal to 19, then x is equal to 5. Now let's prove that's true. How do we start every proof? Let the antecedent. Let 3x plus 4 equal 19. Right? Okay. 2. Then 3x plus 4 is equal to, we can rewrite this as 15. I won't put parentheses there. We can rewrite 19 as 15 plus 4. And that just has to do with the definition of 19.
Okay.
So 19 is the same thing as 15 plus 4, right?
Yeah.
So we replace something identical with itself. Okay, now, then we have 3x is equal to 15. How did we get there? Now we got there using axiom 1. Oh, sorry. Well, you okay with me making that leap there?
Yeah.
Okay. So then 3x is equal to 15. That's using axiom 1. What does axiom 1 say? If I add the same thing to two different things, then those two different things are actually the same. So a plus two different things, if that's true, if a plus something is equal to a plus another thing, then those two things are equal. So here's our a, here's our a, here's our b, here's our c. So b plus a equals c plus a implies b is equal to c.
Yep.
Follow that? Now we're kind of using a dangerous assumption that we didn't explicitly state, and I know why the author didn't, but we're being a little bit fast and loose. We should have added a step in there. This says the same thing as 4 plus 3x is equal to 4 plus 15.
Order matters.
Order matters, typically. How do you know that you can just swap those around? You know for mathematics that you can, but when we go and we restart and we do everything rigorously, order is going to matter, and you can't just be that fast and loose. So the author's being a little bit fast and loose here, saying, well, you already know that when you're adding, this can be the same as that. So, not the greatest exercise that those were in different orders, but you got it. And then from here, then we could have gone to there using axiom 1. Right?
Yeah.
Once again, then 3x is equal to 15.
Right.
And that's just definition of 15. 15 and 3 times 5 are the same thing. And then we can get then x is equal to 5. And what axiom was that using?
2.
Axiom 2. And then we're done. That's what we were after. Make sense?
Yep.
All right, who wants to do the next one? It's going to be almost identical. Let's get the numbers up here. So I'm going to have one person prove if x equals 7, then 4x plus 5 equals 43. It's not 43. Equals 33. I say one thing and think another thing. And then someone else is going to prove the converse. If 4x plus 5 is equal to 33, then x is equal to 7. And why am I going to have you guys do these? The reason I'm going to have you guys do these is because it is so easy for you to sit there and have me walk through these things and say, oh, that makes perfect sense. Oh, that's easy. That makes perfect sense. That's easy. And then you come across a problem where you have to do it and you instantly get stuck. Very common experience. And you're laughing, so I assume that some of you have had this experience. Oh, yeah. So who wants to be the first one to have the experience again? This one's an easy one. That one you don't even have to use the axioms. All right. We got our first volunteer.
So if x equals 7, then...
So let me write out the proof really quick. Proof. If x equals 7, then 4x plus 5 equals 33. Okay, so line 1, what's the first thing I write here?
So let x equal 7.
Perfect.
And then... I'm stuck on that one.
Okay, so what are we trying to show? We're trying to show 4x plus 5 equals something, right? So then, what is 4x plus 5?
4 times 7.
There you go, so just replace that x there. So 4 times 7 plus 5. How do we know we can do that? Up here, x is identical with 7, so I get to replace an x with the 7, and I haven't broken any rules. Perfect. Now what?
Then 4 times 7 equals 28, plus 5 equals 33.
28 plus 5, add on the 33, or add together and you get the 33, and there we go. So the youngest one in the class is the first one to do it. And she did it right! Right? That's not bad. Okay, who's going to do the converse now?
I will.
Alright. If 4x plus 5 is equal to 33, then x is equal to 7. You can come up and write it. That way I don't have to stand there too long.
So we start with let 4x plus 5 equal 33.
Good.
I won't write this as up another step, but this is like equivalent to 4x. Oops. 8 plus 5.
Okay. So 33 is the same thing as 28 plus 5.
Right. And then this is by axiom.
That one's 1. 1 for plus, 2 for multiply. You good with that? So just cancel out the plus 5 from both sides.
Yep.
Using the axiom. Good.
And there's not an axiom for that, it's just the algebra that we're going off of.
Just definition of 28 is the same thing as 4 times 7. And we'll show how to prove stuff like that here in a sec, but show basic.
And this is by axiom 2. I don't think I have to clarify anything else there.
Yeah, good. Who remembers what that back and forth arrow is?
Is logically equivalent to?
Yeah, logically equivalent to. Perfect. So that is logically equivalent to that. And that's what she's saying over and over there. Any questions about anything she did there? Made perfect sense. That wasn't bad, right? Right, Chandler?
Yep.
We'll have you do not the next one, but the one after that, because the next one's probably too easy. All right. Let's see what the next set of exercises are. So we did that one, we did that one. I don't know, you can do this one. Alright. So you're going to prove if 7x plus 9 is equal to 65, then x is equal to 8. And you probably don't have a lot of experience even writing proofs, right? So this will be great for you start to finish. Give you the right syntax so that when you come take my classes, you already know. Okay, which one am I using? Whichever one you like. So just syntax. I guess that's fine. So typical syntax when you're writing your proof, you do proof with some colon and then underline the statement that you're proving, and then you start one let. You won't often see the one let. That's just my own particular flavor.
Okay.
So start with the proof, the statement that you're proving, even though I have it written right there.
Didn't you used to do observe instead of let?
You do
Depends on
let
the proof.
when you're defining something. You do observe when you're using something you've already proved. So I say let x equal 2, observe 2x equals 4.
Right.
Alright, so we got proof, implies, okay, he said the implies instead, that works great. So 1, let 7x plus 9 equals 65. There's no colon after the let. Perfect. 2.
Go one here.
What?
That's wrong.
Yeah.
So
Is equal to what?
Plus 9.
Plus 9.
Plus 9.
Okay. So those are 9s, not 4s. I'm with you. I should look at my initial one. Okay, so 7x plus 9 equals 65 implies 7x plus 9 is equal to 56 plus 9. Okay? So then 7x plus 9 equal 56 plus 9 is logically equivalent to,
That's how you do it, right? The A one.
but it's not that they're equivalent. This being true implies this is true. So that's just an over arrow. And that's using axiom 1. Axiom 1 says if this, then this. Okay.
Isn't it technically both ways with the logic
It's-
L1 that you have up there?
It's technically true, but it's not what axiom 1 says.
Oh, fair enough.
Perfect. Not too bad, huh?
Yeah, that was.
Pretty sure that problem's at conversely as well.
We won't talk about that.
Yeah, the converse of that one's real easy. Alright, if and only if. Alright, who's gonna do this one? Oh, that's only if. That's not if and only if. I read that wrong. You remember which way the only if works? Which of these statements is the antecedent? The left one or the right one?
The right one.
I thought it was
Raise your hand if you think the left statement is the antecedent. You're all wrong. The left side is the antecedent. The right side is the conclusion.
No, because
that is true.
Alpha, oh, down here. Alpha only if beta says the same thing as alpha implies beta. Alpha if beta says beta implies alpha. alpha if and only if beta does it both ways. This is a language that's going to get you confused the most probably. This is why we go all the way back to logic to make sure you understand these things. Alpha if beta says beta implies alpha.
Yeah.
Donnie will wear shoes if it rains outside. Means if it rains outside, then Donnie will wear shoes.
Okay.
Right?
Okay.
Alpha only if beta says alpha implies beta. And the example that seems to work the best for this one is there's fire only if there's oxygen. Means there's fire implies there's oxygen. You know you can't burn something if there's no oxygen, right?
Yeah.
Okay. So it's true that if there's fire, then there's oxygen, right?
Yeah.
Right? Now I'll read this one. There's fire only if there's oxygen. It means if there's fire, then there's oxygen. You see how that says the same thing as that? Okay. And so now when we say alpha, if and only if. So notice the top one says that implies that. This one says that implies that. Together when you say alpha if and only if beta, that means alpha implies beta. And beta implies alpha. Or in other words, alpha implies beta and beta implies alpha. Back and forth arrow. They're logically equivalent. If this is true, this is true, and if this is true, this is true. So they have the same truth values. And you remember how we shorten this? How do I write that on paper so I don't tire my hand? IFF, 2F's. So we would have written that alpha IFF beta. And that's shorthand for if and only if. And you'll see that a lot.
So that's, there's a fire if and only if there's oxygen.
Well, that one happens to not be true.
Oh,
I was just giving you intuition for how this says the same thing as this. Because usually that's the one that's hard for the students. This one they're usually okay with. It's this to this that tends to get confusing.
You didn't go over only last week.
No, I went over it the first week of class when we were doing propositional logic. So, lots of explanation in the first lecture. If any of that's confusing you, we spent a good amount of time on that. Talked about how implication is the hardest one to get intuition for, and how it's going to confuse you over and over again. Okay, so now 5x plus negative 3 equals 27 only if x equals 6. Is the antecedent on the left or the right? The left. Okay, so we're saying this implies this, right? Okay, who wants to do that one? Oh, I better write it really quick. 5x plus negative 3 equals 27 implies x equals 6. All right, who's up? All right, Peter. All right, so we start with let our antecedent come when you start a proof. All Alright, 27 is identical with 30 plus negative 3. They'll say the same thing. Okay. Any questions on what he did on any of those steps? All of that makes sense? Then, comma, using A1, comma, 5x is equal to 30. Helpful. You might think I'm nitpicking there, and I'm going to pick on Peter a little bit because he has more experience than you guys writing proofs. Every line in your proof should be a complete sentence. If you can't read it as a complete sentence, you mess something up. And notice how he's had it here, even though we all understood what he was saying, because we just seen a bunch of these. If you came across this on paper, then using A1 implies 5x equals 30. Then using A1, 5x equals 30.
Yeah.
So when you're writing your proof, each line should be a complete sentence, and reading it out loud should make perfect sense.
Is
So-
number 4 right? So,
Yes. Then 5x equal to 5 times 6 implies x equals 6, using axiom 2, and parentheses at the end there makes perfect sense.
Never the square.
Never wrote the square, signifies that's done, but
Actually, I haven't gotten out of it, never write the square. I think I wrote like twice in discrete.
I do the one thing I remember.
you're looking forward to putting that square on paper. Feels so good every time you do it. Okay. Getting to the harder ones. All right, some more of that language we covered first week. Necessary and sufficient. X equals 11 is a necessary condition for 5x plus 4 equals 59. Is the antecedent on the left or the right?
On the right. The left.
Raise your hand if you think the left. Let's see if people just start voting. Raise your hand if you think the right. And it's the right. This being true implies this is true.
But,
Sufficient is the other way.
Oh, okay. Sufficient makes sense.
I don't understand the word sufficient then, because I think if sufficient was there, then I'd choose the right still.
Is oxygen a necessary condition for fire, or is fire a necessary condition for oxygen?
Oxygen is a necessary condition for fire.
Oxygen is a necessary condition for fire, means alpha implies beta. Oh, sorry, backwards. I need to label these as something.
Fire and oxygen.
Yeah, so I'll just use that. So if there's oxygen, or if there's fire, then there's oxygen. So fire implies oxygen is the same thing as oxygen is a necessary condition for fire.
Okay.
What about sufficient?
There being fire implies there's oxygen, one at a time. There being fire implies there's oxygen.
So,
Says the same thing as oxygen is a necessary condition for fire. Here we had the word necessary. So our antecedent was over here on the right.
right.
Everyone follow that? Okay, now let's think about sufficient. Think about the word sufficient. Is oxygen a sufficient condition for fire?
What does the word sufficient mean?
If you know there's oxygen, are you guaranteed there's fire? Is it sufficient to know that there's oxygen to conclude that there's fire?
No.
Do you have enough information? Is it sufficient?
You don't have enough information.
There's fire. Is there being fire a sufficient condition for there being oxygen?
Yeah.
Yes.
Yes.
Okay.
So sufficient condition. So fire is a sufficient condition for oxygen. Oxygen is a necessary condition for fire.
Okay.
Make sense? So tricky verbiage. Tricky until you get it. And so another way people say if and only if you were in like a more philosophy type class, the common terminology they use is it's a necessary and sufficient condition. Alpha is a necessary and sufficient condition for beta. Is the same thing as alpha implies beta and beta implies alpha. Is the same thing as alpha if and only if beta. All say the same thing. Good? So, looking at this one more time. X equals 11 is a necessary condition for 5x plus 4 equals 59. Which side's the antecedent?
Right.
The right. And then, so this is a conclusion. So we're saying 5x plus 4 equals 59 implies x equals 11. Alright, who we got for this one?
I'll do it.
We'll ask Les to do this one.
Fine, I'll do the easy ones.
Yeah, we'll make you do, they're all easy. You can show how to do an if and only if proof. Oh, you haven't done that. I keep thinking you're in discrete math.
I can do it.
Alright.
Or Emma can do it. Preferably Emma.
Well, once we get all of you guys doing one, I'll probably just finish them off.
Bigger.
Proof. It's a good recommendation. Remember, there's people on the internet watching you, learning from you. Yeah.
Just one or two. Don't worry.
All right.
It's all 12 views.
Well, no, this one's gonna get like 20 because you guys are gonna go back and watch yourselves. I just know it. All right. So let our antecedent, then capital T, your starting sentence.
Is that 11 or 4?
Sorry, that's an 11.
Okay.
I'm as bad as Chandler.
Should I?
You can just ask yourself which one makes sense really quick, right? So 5x plus 4,
Can I go straight to?
55 plus 4 again. Because 59 and 55 plus 4 are the exact same number. So you just substitute it, and you're missing a period. Make it so small it can't be seen. I love it. Alright, so then, that way you can do all the work and don't get any of the credit.
Well, they can't read it and they just assume it's right.
Or they can't read it and assume you messed up. Good. So by axiom 1, the left-hand side implies the right-hand side. Just so you know, you're getting smaller as you write. Got plenty of whiteboard space. Big. There we go. Good. So 5x is equal to 55, then 5x is equal to 5 times 11, since 55 and 5 times 11 are the same number. Appreciate you double checking that. And period, and then your big box. And there it is. And thus it is demonstrated. Wonderful. All right. And Jeremy, you got the next one. You can go write it and erase and stuff. I'll just keep sitting here.
I don't know what the comma means. What does the comma mean?
If x equals 11, 5x, comma means take a pause. So read out loud. If x equals 11, 5x plus 4 equals 59.
It's basically a then.
Yeah, it's a then. The author's trying to give you all the common ways we say things in English so that you know how to convert it into implication and then prove it.
Right.
What's that?
Okay.
Oh yeah, you're doing it. You remember what it is?
Nope.
Okay.
I was gonna write it while it was there and then we could do it.
All right. So prove
So write it twice.
x equals 11. Then 5x plus 4 equals 59.
5x plus 4 is 59.
Oh, we gave you a easy one. Oops.
This is just like all the rest of them.
No, this is one where you don't have to use any axioms.
Why not?
All right, keep going.
Is it the same thing?
Nope, they bend the other direction. They were of the form if 5x plus 4 equals 59,
Oh, that's right.
then x equals 11.
Antecedent.
X equal 11, period.
Let's see. If x equals 11, then 5x plus 4 equals I don't know if I'm skipping these steps.
So no, you're not skipping a step. We know from identity that x is identical with 11. So you have identical statement on either
So
side.
it's just straight substitution.
Yep, just straight substitution.
You're right,
It's
it's
just
just
logic.
easy. So we have to be.
You can just continue on that one line if you want, is equal to da da da.
That's right. Equal to
There you go.
that's the end.
And that's the end. That's it. You're just showing that if x equals 11, 5x plus 4 equals 59. And you showed it.
Easy.
Yeah. Alright, so has everyone done one?
Not James.
Not James? Alright, James, you got the last one. And you got the if and only if.
That means you gotta prove each case.
Yeah, go first.
Oh, and you got a super weird one.
Yep.
You can just do one direction on that if you want, and then I'll do the other direction, since it's already weird enough.
Okay, so prove. I see why Lester wrote small. It's not a marker.
No, but they finally got good sticks of chalk.
Took them long enough.
Yeah, it did take a bit. They went and found a new brand. Not sure who found it. Sergeant Art.
Sergeant Art.
Yeah, Crayola used to be good, but now they're garbage, so I have to find new ones.
So because if and only if. Is
Yeah,
that-
just pick one direction
right.
first. and
Then
then-
I'm gonna go this way first.
All right, so he's going to show that the left implies the right.
One. Let 2x plus 7 equal 19.
Okay.
Nice. don't even know where to begin. 2.
Well, if 2x plus 7 equals 19, what's x?
Oh. Okay.
Yeah.
Okay. Then 2x plus 7 equals 12 plus 7. Then 2x equals 12
How do you know?
because of assumption
Alright.
4. Then 2x, I should have just kept going, equals 2 times 6. And then by assumption 2, you get x equals 6
Using 2.
using 2. Now, think about this.
Okay, so now you know
Now I know
that
what
if
x
2x plus 7 equals 19, x equals 6. But does that mean that 4x minus 3 equals 21?
Then
Then what is 4x minus 3?
four x minus 3. I don't understand. Do I just repeat the process?
No? Figure out what 4x minus 3 is. Then write 4x minus 3, and I think you'll start figuring it out as you go. And 4x minus 3 equals what?
Then I substitute x.
And there you go. Yep. Sometimes you don't see it until you start writing, and then it becomes obvious. So, and something about writing on a whiteboard in front of people.
Yeah.
You can
About other things and not the problem.
Equals 21.
Perfect.
But what does that use? Just arithmetic?
Yeah, definitions of the numbers. It's using the definitions of the numbers. Okay, so common pattern when you're proving an if and only if proof. You need to show this being true implies this is true, and you need to show this being true implies this is true, right? So common things that you'll see in proofs like this is they'll typically start with an arrow like that to say, hey, I'm going to show that this one implies this one first. And then after they do that part, then they come here, and then you'd see another arrow pointing the other way, like that. And then they do 6, and then they start it out with, now this time we're going to let 4x minus 3 equal 21. Right? Then we do 7. Then 4x minus 3 equals, we can rewrite that as 24 minus 3, right? Which is the same thing as, if we want to be super explicit, 4x plus negative 3 is equal to 24 plus negative 3. Right? 8. Then 4x is equal to 24. That's using axiom 2. Right?
Axiom 1.
Axiom 1, yeah.
Oh, axiom 1, thank you. For some reason I thought I got rid of a multiplies term. Nice to see you're paying attention. Then we get 4x is equal to 24. Then, yeah, kind of taking too much vertical space here, huh? And that implies that x is equal to 6 using axiom 2, right? If 4x is equal to 4, 6, then x is equal to 6. Then 2x plus 7 is equal to 2x plus 7 is equal to 2x plus 7 is equal to 19. And we're done, because we proved it both directions. So that's typically how you do an if and only if proof. It's basically just doing two proofs wrapped in one shell. Nothing special about them. Something weird?
Why did you do 2x plus 7? Because you came up with that.
He did 12, which is 2x plus 7.
I know, but why does that matter? Why are you trying to solve that?
So now I need to show that if this is true, then 2x plus 7 is equal to 19. So I assume that this is true. That's my let right here.
Oh.
And I need to show that if this is true, then when you evaluate 2x plus 7, you get 19. So I took 2x plus 7, I evaluated it, and it was 19. Make sense? Good? Getting a nice feel for these basic algebra proofs you've been doing all your life? Right?
Starting to get familiar.
The same way that your 7th grade teacher taught you? Right? Alright, so we did that one. Let's go to the next ones, do some more interesting ones. Let's only do them if they're interesting. This one seems interesting. How do we do a proof that there is no number x such that 3x plus 11, or that 3x plus 5 is equal to 11, and 4x minus 1 is equal to 3?
You solve for x and you try and find
No, you use quantifiers.
So what does this say?
quantifiers.
This says it is not the case that there exists an x such that 3x plus 5 is equal to 11 and 4x minus 1 is equal to 3. Okay, that one's kind of a toughie, right?
No, because we know the logical implications of and.
Now what we have are, let me just write this a little bit differently. What we have is not there exists some x such that some proposition about x and some other proposition about x.
Oh.
That's what we have, right?
Yeah.
Just writing it in propositions. So now using logic, we know how to distribute a not across a quantifier. We did a theorem last time, right to the side here. We proved that not there exists x, some proposition about x, is the same thing as, this is logically equivalent to, for all x, not that same proposition. You remember that? And we also proved vice versa. We proved not for all x, some proposition about x is logically equivalent to there exists some x such that not that proposition about x. So what does it say? This says if I want to put that not, get rid of the not here, if I want to distribute that through, I switch this to a for all, and I take the negation of this whole thing. And so we also had a proof last time, you might remember this one, not alpha and beta, when we do a not across two propositions, that's the same thing as not alpha or not beta. You remember that? And similarly, we showed that not alpha or beta is logically equivalent to not alpha and not beta. So we're going to have to use this one and this one to even figure out how to go about proving this thing. Right? So we need to show then, distribute the not through here. That turns us into for all x, and then we need to do not p of x and q of x, right?
Oh.
I'm breaking it up into one piece at a time.
Yeah.
And now when we distribute the not across an and, it switches the and to an or. So this is the same thing as, well, I guess I can just write down here. For all x, not p of x, or not q of x. So I need to show one of them is false. So I need to show that for any x you choose, either this is false or this is false.
But don't you have to have an implication to do your proof? You can't just prove this or.
So we're going to have to do two proofs in here, kind of. I'm going to have to say pick an x, show that if this is true, then this is false. And if this is true, then this is false. Therefore, one of them has to be false. We have four possible cases here. P and Q. We can have true, 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 false, false, true, false, false. Of these four possible cases, which one of them satisfy this? We need this one's false or this one's false. So that's covered by these three cases, right? So I need to show us one of these cases. If I show that this being true implies this is false, then how can I say this better? If I show that this one being true, if I show that P being true implies Q is false, if I show P implies Q is false, there we go. Let's think about it that way. So here's P implies Q. Here's Q implies P. Okay. P implies Q. Let's write out the true table for that. Does true imply true? Yes. Does true imply false? No. Does false imply true? Yes. Does true imply true? Or does false imply false?
Yes.
True. Okay, let's look at the converse. Does true imply true? Does false imply true? Does true imply false? No. Does false imply false? Okay. So if I can show, thank you. If I can show P implies Q is false, and Q implies P is false, then that means P implies Q is false or Q implies P is false, then we have to be on one of... No, that's still not a good way to say it, is it?
Isn't there a way to turn an or statement into an implication?
Yeah, there is, and I was trying to avoid that, but maybe that's the best way to redo this. Okay, so another piece of logic rather than trying to make my messy table that we're doing here. Could have left the... Come to think of it, that's a better way to think about it anyways. I should just start there. Good call. Alright, so let's look at P implies Q, and then let's look at not P or Q. And it turns out these say the exact same thing. So we're going to prove that really quick, and then we'll write that as one of our things down here, that alpha implies beta is logically equivalent to not alpha or beta. You with me? Okay, so we can have true, 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 false, false, true, false, false. You guys just really told me these ones, so I'll just write it really quick. Right? Okay, so now let's fill out this column. Not P or Q.
True.
True. It's true because this one's true. We're oring these two together. True or true is true. Or sorry, false or true is true because it's not P. Everyone follow that? Okay, what's the value here?
False.
False. Not P or Q is false. False or false is false because that's a not P and this is P. Everyone follow that? Okay? And now, true or true is
True.
true, and true or false is true. True or false is true. And notice now, true, false, true, 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 false, true, true. They have the exact same values for the same inputs. They always do the exact same thing. So they're logically equivalent. These are all the possible combinations. There's only 4 possible combinations. And for any of those 4 possible combinations, they always do the exact same thing. Therefore, they are the exact same. Make sense?
Yeah.
So, Emma's right, that's a better way to think about it. So not alpha or beta is the same thing as alpha implies beta. So applying that here, my alpha for this substitution, my alpha is going to be p of x, and my beta is going to be not q of x, so you can see the substitution. Don't want to lose it here. I'm going to have alpha is equal to p of x, and beta is equal to not q of x. So notice that if we have not alpha or beta, that's the same thing as alpha implies beta. So here we have not alpha. Alpha is p of x. I'm just arbitrarily choosing, I may call p of x alpha and not q of x beta. I'm just labeling them. There's nothing wrong with labeling things, right? I can call it whatever I want. So notice now, we have not alpha or beta. Oh, oops, did I erase a not there? There's a not there. Does everyone see that?
Yep.
So I can rewrite this line for all x, not alpha or beta is the same thing as alpha implies beta. This line says the exact same thing as this line. Weird? Still weird?
1 second. I got lost on like the last 3 sentences.
Okay, come back to the beginning. So we have some proposition or some proposition.
Okay,
Right?
where I'm stuck is you have not alpha in the second line. Okay.
Perfect. Let's do our actual substitution and write that down. For all x, not alpha or beta, doing my substitutions I have it, right?
Right.
And then using this substitution, not alpha or beta is identical with alpha implies beta.
Okay.
Okay, so then we have for all x, alpha implies beta, which is logically equivalent to, for all x,
P of x
p of x implies not q of x. Okay, now is everyone good?
Yeah.
We all see it? Notice how much logic we had to use here even to make sense out of what we were trying to prove.
Right.
We were trying to prove that there does not exist some number x such that 3x plus 5 equals 11 and 4x minus 1 equals 3. That's what we were trying to prove. How would we even wrap our heads around how to prove something like that without using some logic? Now that we use some logic, we see that this is actually asking the same thing as, let's rewrite it out here now, for all x, if 3x plus 5 equals 11, then 4x minus 1 does not equal 3. How much easier is it to make sense out of that thing than out of that thing?
A lot more.
A lot easier. Right?
Yeah.
So we just need to show that if this is true, then
That's not true.
this isn't true. Or what I actually have written there is true.
Right.
Right. So there's our actual statement that we're going to try and prove. I'll erase all this stuff above it, write out what it is we're actually proving, and then we'll prove it. And you see the hard part with this problem is not going to be actually proving this thing. It was figuring out what on earth you're even being asked to prove. And this is similar concepts in any field that you're going to study. These guys taking physics, how many times is the hard part of the problem trying to figure out what the problem wants you to do?
It's usually like
The hard part. Doesn't matter what your field of study is, that's very common that that's a hard part. Or the teacher's giving you a very watered, dumbed down version of the field. That's also possible.
it happens.
It does happen. So now, let's prove that statement. Proof. For all x, if x with 3x plus 4, 3x plus what? 5. 3x plus 5 equals 11. Then 4x minus 1 does not equal 3. That's what we're trying to prove, right?
Yeah.
Okay, so 1. Let x be any value. So pick a random x, any value such that 3x plus 5 equals 11. So pick any random x that happens to satisfy this. And we're going to show that random x does not satisfy this. Or it does satisfy this with the not in there. Everyone with me so far? How do I prove that something's true for all x? I need to show that's true for any x. So I need to grab any x. Let x be anything that satisfies that. Make sense? Okay. 2. So let x be any value such that 3x plus 5 equals 11. Then 3x plus 5 is equal to 11, which gives me 3x is equal to 6. Right? Then 3x equal to 6 implies x is equal to 2.
That's right.
Then 4x minus 1 better not be 3, or we did the proof wrong. Then 4x minus 1 is equal to 4x minus 1 is equal to 4x minus 1 is equal to 7 is not equal to 3. Those are different numbers. And we're done. Good? That was a great proof. That was a great problem, I mean, for us to do. Really bring all that logic back into it. That's why you let authors think up examples. They put a lot of time into those things. Come up with good ones. If you have a good textbook, which just comes from a good textbook. All right?
In a real proof, then you would have to explain why you used all the logic to come up with what you're actually proving, right? So like in a logic textbook,
Depends.
you have
I
those
mean,
labeled.
I don't know what you mean by a real proof. You did logic with us, right?
Yeah, and I also
You remember the big leap in
Exactly.
going from a proof in logic to a proof in algebra?
It's massive.
It was massive. So if you mean a real proof, yes, you need to show all the logic you use if what you mean is a logical proof.
All right.
But we have a lot of shorthand once you're working with people who are comfortable with logic. But no, we're not going to do any proofs as rigorous as like a logical proof. That's pretty intense. And it would take us 50 lines to do something like what we just did.
Right, you have to show each one of those.
Oh, you have to do a lot more than that. I mean, there's a lot. Rigorous proof is a lot. But it's a ton of fun. Anyways. So that was a cool one. All right, let's see what this one. I think we did this one last time. Yeah, we did. What can you infer if it is known that a is not equal to 0 and that a times 3b minus a is equal to a? And I showed that, I proved last time that if a is not equal to 0 and a times 3b minus 8 is equal to a, then b was equal to 3. And I proved that last time. Good?
Yeah.
Do you need to see it again or ready to just keep going? Think you're good? Okay, next one. What can you prove if it is known that r times 7b minus 5 is equal to r?
Even when you don't know that r doesn't equal 0.
Well, this one it doesn't say anything about that. So in this case, we know that r equals 0. I ignored the context. I didn't give you the context for this. Oh, it's right here. We were always talking about integers. And 7b minus 5 isn't an integer.
Yeah.
I can't take an integer, multiply it by 7 and minus 5 and still have an integer. So it's impossible for this to be 0. And it's impossible, this right here isn't even an integer. There's no integers that make this true. That's a better way to say it.
Yep.
Unless r is equal to 0. Then there are integers that make that true. For example, plug in, give me any number for b you want. 1. Give me a better number. If I know that r times 7 times 2,586 minus 5 is equal to r, then I know that r is equal to 0.
Okay. Alright.
Right?
Just because of the numbers.
Because that's not an integer.
Alright. But the one before it was.
So if this statement's true, I know that this right here can't ever, I shouldn't say that's not an integer,
We said
sorry.
the problem before it.
This isn't ever 1. Why do I keep saying an integer? I think one thing, say another thing. It's impossible for 7b minus 5 to be 1.
Right.
So it's a number that's not 1. And so r times something that's not 1 equals r only works when r is 0. So that was kind of similar to the other one. Let's look for a more interesting one. What can be proved if it is given that 3a plus 12 times 2b minus 8 is equal to 0, and b is not equal to 4? So let's try that one out.
Can't you just make a equal to 0?
You can't make anything. You can only use what's given to you. Prove that if 3a plus 12 times 2b minus 8 is equal to 0, and b is not equal to 4, then what are we going to prove? We're going to prove that a is equal to negative 4.
No, that's not too
So that's what we're going to prove here. Not too hard. You want to do it?
Yeah, it does. 2a.
I'll let you do it if you want.
They always say this.
Not me. And b does not equal 4.
Oh yeah, and B doesn't equal 4. Thank you, James. So all I'm trying to get is a is equal to negative 4, right?
Well, that's going to be the final thing you prove, yeah. When it's all said and done. So you're going to sit there and manipulate the
I wanna
expression
manipulate this
over and
thing,
over
right?
and over again until you're left with just an a on the left-hand side, and you'll be left with a negative 4 on the right-hand side.
Wouldn't I want to distribute it then?
You don't know anything about distribution. There's no rule that says you can distribute. What are you talking about?
And I can only use these, right?
Correct.
You could.
And you can use basic
Can
definitions
I
of
help
numbers.
you?
Yeah.
What's your big idea?
My big idea is to make what times 0 equals, or my big idea is to use the assumption 2.
The bottom one?
Yeah,
Well, we're not going to use that one yet. We need something on the
Yeah.
right-hand side to make so that we can use that.
We need to move something over.
I don't know about move.
look, make the left parentheses A and the right parentheses B, and make
So you're saying
0
let this
A.
equal A, let this equal B?
Yeah, and then make 0 A,
You already have an A and B there. You can't just redefine them.
But alpha or beta?
alpha and beta.
Okay, so view this as we have alpha times beta equals 0. Then what?
then
Yeah. What can you do with that?
alpha times beta
The
equals
axioms
0.
only apply when
Then
you, will you put a C there? in the
alpha
bracket?
times C.
Fix that.
Yeah, right there.
You gotta get something to cancel it out.
Yeah, you have to have something on the other side.
Yeah, so how do we get something on the other side?
Rewrite 0.
You rewrite 0.
That's what I was trying to say. Is rewrite 0.
As what?
I just didn't know the words.
How do you rewrite
As
0?
2 times b.
As 2b
What's that? Is that a plus or a minus?
minus.
2 times b minus a times 0.
Okay. Yeah,
That
you have
is
the
what
right
I was
idea.
trying to say the whole time.
Alright. So 0 times
0 times.
2b minus 8.
Right.
0 times. Oh, I see.
There you go. So yeah, you had the right idea.
I don't know
Rewrite
what
0
to say.
as 0 times 2b minus 8. Okay, no alpha or beta
So,
rewrite.
well, you can just use definite axiom 2 here, right? But do you want me to be explicit and say, let 2b minus 8 equal beta, and let this equal alpha?
Oh, that's just a symbol. Look, you have a symbol times a symbol equals 0 times a
Yeah,
symbol.
I'm saying, do I need to explicitly make this something, or can I just say
No,
it?
no, that's a symbol. It's a symbol with a couple characters in it,
So
but it's just a symbol.
That just implies 3a plus 12 equals 0. By axiom.
Yes.
Y'all got that?
We losing you? Alright, let's go from this step to this step really quick. What's 0 times anything? 0. So this is 0, and this is 0, right? So we didn't break any rules. We just wrote 0 a different way. Right? It's just another label for 0. A bigger label, but still just 0. And now we have some symbol times some symbol equals some symbol times that same symbol. Those two symbols are the same. Axiom 2 says you can drop both those symbols and you're still good. So we're just dropping both those symbols. Doesn't matter that they're all those things. I could have put a SpongeBob there and a SpongeBob there and cancel out the SpongeBobs. It's still perfectly valid. Any symbol. Just cancel it out. Whoa! What did you do there?
What do you mean, what did I do?
Where's a rule that says you can just take a 12, shove it to the other side, and put a negative sign there?
So I need to do the same thing,
Yeah, rewrite the 0.
and I want to rewrite it as what, 12? Yeah?
You want to isolate A. So just keep playing with it until you isolate A.
Is then equal to
0
times 12,
Times 12.
No,
That's not
0
gonna work.
plus
0 plus 12.
plus negative 12.
Except ignore the 0.
Yeah.
12 plus negative 12 is 0.
So you're saying like that?
Well, I
I
guess.
said that,
Yeah, that works.
That's,
but well, you
Right?
do.
yeah, that's
Then I
rewriting
can cancel
0.
out these terms, and then I'm left with the negative 12.
Okay.
Okay.
But now you just use one of your axioms to do that. So keep track of that fact.
Yeah.
And just so that we're not being too crazy, let's get rid of that 0 symbol. So it's very clear what you're doing.
Okay. And then this is just 3a is equal to 4 times 3, which implies a is equal to negative 4.
Which is what we were after. Okay. So maybe rather than having you talk it, we should just have you come up and write it next time.
Right.
Sounds like you had it figured out from the start.
Yeah,
Cannot
dude, why did I
explain.
get up there?
All right.
Have to rewrite the 0.
The next one's not too much different. It is known that 2a minus 3 times b minus 3 is equal to 2a minus 2. Prove that a equals 1 implies b equals 3. Prove that a not equal to 1 implies b not equal to 3. So maybe we'll just do the bottom one. I can talk you through the top one really quick. The top one says, prove that if I plug in a 1 for A here, and then isolate B, I'll end up with B equals 3.
Okay.
So that one's not as interesting, but here's a more interesting one. Prove that if A is not equal to 1, then B is not equal to 3. That one's a bit more complicated.
Okay.
Okay? So how are we going to do that one? Let's think about that one for a second. So let's write out what we're trying to prove. So, given 2a minus 3 times b minus 3, was it minus 3? Yeah. Is equal to 2a minus 2. That's given. If we want to show that if a is not equal to 1, then b is not equal to 3. Oh, thank you. Did I get it all up there? All right, so how are we going to show if A is not 1, then B is not 3? How do I plug not 1 into that thing? What's our big idea, not Emma?
There exists.
I mean, over here, I'm trying to show that A not equal to 1 implies B not equal to 3. That's hard to work with. Can we use any nifty logic to rewrite that in a way that's more workable?
Yeah.
How can we rewrite it?
Not b equals 3 implies not a equals 1.
It's basically the same thing.
I think you have the right idea, you're just saying it funny. So you're telling me not B equals 3 implies not A equals 1?
Not like you know.
Not. He's
You
not.
nodded. So show that B equals 3 implies A equals 1.
Yeah, that's right.
Yeah, you want to nod him. So what's he using there? He's using what we called the contrapositive. Alpha implies beta says the exact same thing as not beta implies not alpha. If we write out the truth tables for both those things, they give the same values, and we already showed that. So here we had if this is not beta implies not alpha, then that's the same thing as alpha implies beta. You see that? Another very useful thing to keep in the back of your mind for when you're doing proofs. Because you come across stuff like this all the time. So we want to show that if B is equal to 3, then A is equal to 1. So, 1, let 2A minus 3 times B minus 3 equal to A minus 2, comma, and assume B equals 3. Okay. 2. Then 2A minus 3 is equal to 3 minus 3 is equal to 2A minus 2, right? Just substituting in B with 3.
Yeah.
Good so far? What's 3 minus 3?
0.
Perfect. And what's anything times 0?
0.
So then, I won't bother with the line in between, we'll just go fast. So then 0 is equal to 2A minus 2, which is the same thing as 0 is equal to 2A minus 2. Okay, so now we finally use an axiom. So then, 2 is equal to 2A using axiom 1. Right?
Yeah.
Then 2 is equal to 2A, which gives us that
A equals 1.
A is equal to 1 using axiom 2. And we're done. Good? Not too fast? Alright. Awesome. So that's the end of our exercises.
That
And now-
proves that proves that A does not equal to 1, then B does not equal 3.
We just barely showed that if B equals 3, then A equals 1. That is the exact same thing as not A equals 1 implies not B equals 3. Those are logically equivalent. I mean, I can add one more line here. Therefore, if you're worried your reader won't get it, therefore, A not equal to 1 implies B not equal to 3. If you're worried that they weren't following exactly where you were going with it. I mean, the answer is always give enough information that the reader can follow you. And a good rule of thumb is assume the reader is your fellow classmate. Okay, good? Okay, so this was just practicing with a couple axioms. And now we're going to get into the actual axioms that we use in algebra.
Okay, so we
And they're not these two. You still can use this in algebra, always and forever. You can always use this. But these are not the two axioms in algebra. We just pretended that those were axioms for a second to play with some stuff. Now I'm going to actually give you the axioms of algebra. A bunch of them. Unfortunately, you don't get all of them. There's one that you don't explain to students unless they're in calculus.
But it's in algebra?
You use it, but you use it behind the scenes, and you never make it explicit.
Can you write it out just for the calculus students?
Oh, I said calculus, I meant real analysis. Sorry. It's what I called. So James has seen it, and Emma has seen it. And it's called the completeness axiom.
That's no fun.
And it says that every subset of real numbers bounded from above has a least upper bound. That's the principle. There you go. That's what it says. And to make sense of that or how that's useful, no point in me trying to do that for you right now.
Okay.
So you won't ever come across that one. Sorry. And it's the one that gives us irrational numbers. So you'll just have to take my word for it. There's irrational numbers, like the square root of 2. So, axioms. And away we go. We're done with logic, and we gotta start some actual algebra.
There we go.
Yeah. Okay. So, we are talking about some mystery set. Some mystery set, we're going to give it that fancy symbol, R. The way I'm going to write it on the board is R like this. We're talking about some mystery set. What's in there? I don't know. And I'm going to tell you a few things about that mystery set. I'm only going to tell you these 10 things about that mystery set. And then we're going to figure out what else we can conclude about that mystery set. You with me? Okay. So, here's the first thing that we're telling you about that mystery set. I'm telling you that if X is in there, and if Y is in there, then this weird thing, X plus Y, whatever that means, is also in there. And we're going to call it their sum. Okay. So if X is in R, and if Y is in R, then X plus R, whatever that weird thing is, it's also in R. You with me?
Yeah.
So, for example, if I know that 1 is in R, and I know that 0 is in R, then I know that 1 plus 0, whatever that is, who knows, some mystery thing, is also in there. Furthermore, I know that if X is in R and Y is in R, then X dot Y is in R, whatever it is. No clue what that thing is, but whatever it is, it's also in R. So, 1 times 0, whatever that is, who knows? I don't have a clue. Do you have a clue? Whatever it is, it's also in R. Okay? So let me read what we're starting with. For each pair of numbers, real numbers, numbers in that set, we're going to call the things inside that set, we're just going to call them numbers. What does it mean to be a number? It just means you're in that set. It's a mystery set. And the things in the set, we're just going to call numbers. Why? Because it sounds cool. So for each pair of numbers, X and Y, there exists a number, another thing in the set, called their sum, denoted by x, and we call that plus for some reason, x plus y, and a number called their product denoted x with a dot y. Hopefully you can see that dot, it's kind of small. We don't, when you get to big kid math, you stop writing 6 times 5 like that, and you just do a dot, because you use x's as variables so much that it just gets confusing. So we're going to use dots for multiplication, never an actual x. Okay, and whatever these weird operations are, this dot operation and this plus operation, whatever they are, they satisfy these 10 rules. And that's it. That's all we're going to assume. And we're just going to derive all the rest of algebra from these rules. Weird. Well, 2 more rules that we'll talk about a bit later. But this is almost all of them. It's the majority of them. So the first thing that we're going to assume is whatever weird number x plus y gives you, whatever that number is, y plus x is the same number. So for all xy, x plus y is equal to y plus x. That's an assumption. Now we're making about that plus symbol. There's other operations out there where this is not the case. We're assuming it's the case here. For that weird symbol. Good so far? Next, we're assuming that whatever weird number, notice x plus y now, I know that's a number. So if z is also a number, so if z is a number and this is a number plus a number is always a number. You with me? So if you have this number, then that's the same thing as if you have this number and you add it to this weird number. So this number plus this number equals this number plus this number. Okay. So names for these rules, because we use them so much, we have common names for it that you'll get used to as time goes on. X plus y equals y plus x, that is called the commutative property. So we say addition satisfies the commutative property. This one right here, x plus y plus z is equal to x plus y plus z, we call the associative property. I can associate these two together and then do that one, or I can associate those two together and then do that one. You with me? So that's what this one says and this one says. Let me jump down for a second and show you that this one and this one say the exact same thing as these two, just with times instead of plus. X dot y is the same thing as y dot x. Whatever that number is, doesn't matter if you do x dot y or y dot x, you get the same thing. Similarly, x dot y dot z is the same thing as x dot y dot z. Same thing. So both addition and multiplication are commutative. Both addition and multiplication are associative. Is how we say that. Good so far? Okay. New thing we know. We're being told there's actually something in that set. There exists something in that set we call 0, such that for anything else in the set, that thing plus 0 gives you back that thing. So now whatever this set is, we know, hey, at the very least, there's a 0 in here. So now we know at least one number. We have one number so far, 0. That's the only number we know so far. You with me? And we know that if I take 0 and I add it with anything, I get back that same thing. So 0 doesn't change what you add it to. You get back the same thing. You get back itself. And so we call 0 the
Identity.
Which identity?
On addition.
We call it the identity on addition, or the additive identity. It's the additive identity because when you add with it, you get back identity, yourself, the same thing. That's why it's called that. We talk about tons of identities in math. Two that you're very comfortable with are the additive identity, and then down here we also have the multiplicative identity. There exists some other weird number in there. We'll call it 1. So now we know about 2 numbers in there. Whew, getting a big set. And we know that there exists something in there, we'll call it 1, such that for any other number, 1 times that number just gives you back that number. So when you multiply by 1, it gives you back the exact same thing. When you add by 0, it gives you back the exact same thing. So 1 is called the multiplicative identity. Or the identity on multiplication. Multiplicative identity, same thing. You with me? Now how do I know that 1 and 0 aren't secretly the same number?
minus.
Well, we have to be told that, and that's right there, down at axiom 10. Because you can't just assume that they're not the same number. You don't get to make any assumptions that aren't explicitly given to you. Just because I use different symbols doesn't magically make it different numbers. You know from later courses, how on earth is that the same thing as that? That's some weird funky symbols and that's just one symbol. And yet you're telling me those are the same thing?
Get over it.
Yeah, so, yeah, that's the same thing. Don't be so sure that those two aren't the same thing. So I have to tell you that they're not the same thing. That's the only way you can know. The fact that they use different symbols means nothing. We can write it, the same number infinitely many different ways. Okay, so we've covered a few of the axioms. Let's cover this one next, I guess. This one's a weird one. This one tells me, sorry, we're on this one. This one tells me that for any x, for any number you pick, there exists some other number such that when you add them together, you get the additive identity. For any number, there exists some other number such that when you add them together, you get the additive identity. Maybe there's 2, maybe there's 3, maybe there's 100, but we're guaranteed there's at least 1. For any x you choose, I'm guaranteed that there exists at least one y such that their sum gives me the additive identity. And so we call y an additive inverse of x. It undoes x to get you back to identity, the additive identity, 0. Similarly, down here, we have something similar. For any x, as long as you don't pick that funky circle-looking symbol that we call 0, for any x that's not 0, there exists some y such that when you take their product, you get the multiplicative identity. Good? And in that case, we call y a multiplicative inverse of x. It undoes x to get back to 1. Finally, what do you do when you got weird plus symbols and weird dot symbols all mixed together in the same expression? That's what this last one tells us. If you've got a dot across a plus, you can distribute it, is what we call a distributive property. We say multiplication distributes across addition. Good? There we go. I just gave you basically all the rules of algebra. You just apply these rules, that's all you do in algebra. I don't care if you're talking about pre-algebra, algebra 1, algebra 2, college algebra. In fact, that's all you're doing in calculus. Same thing. You're just applying these rules. There's 3 other ones that we haven't listed. We'll talk about 2 of them. One of them you don't talk about unless you're in calculus. But that's it. All those different math classes that you go and you take in school are all just dealing with these couple of assumptions. Not bad, right? You can do that. You can do algebra. You can do calculus. You just have to know what 13 statements mean. These 10 and 3 more. That's it. That's easy, right? And then you just do with these 13 statements what we've been doing before. So should we start playing with these 13 statements? Sure? Well, since Jeremy said it. All right. First off, before I start playing with them, I want you to notice how we already can start defining new numbers now. Okay, so before we even start proving other things, let's just start talking about some numbers. So I know that this is a number now, right? That was given to me. I know that there's a 1.
Yeah.
Okay, so what about if we look at 1 plus 1? I'm guaranteed that that's a number. Now, is that a different number from what I already have in here? For example, do I know that 1 plus 1 isn't really the same thing as 1?
No.
How do I know that 1 plus 1 is not the same as 1? We got to prove that this number is somehow different from 1. Right? So should we do this proof really quick?
Yep.
Okay, let's do a simple proof with numbers. How do you know that 1 plus 1 isn't 1? Make your math teacher prove this to you. Proof. 1 plus 1 is not equal to 1. We can prove that's a new number. Observe that, I didn't give myself a lot of room to write here. Observe, so you're going to have to get with my shorthand notation. There exists a y such that 1 plus y equals 0. What axiom did I just use there?
Additive fourth.
We just used this one. This one says that for any number, there exists some y such that when you add them together, you get 0. Is 1 a number?
Yeah.
So then I'm guaranteed there is something out there y, some mystical symbol, I don't know what it is. But whatever it is, I know when I add 1 to it, or when I add to 1 I get 0, right? So 2. If 1 plus 1 is equal to 1, then 1 plus y is equal to 1 plus y. Adding the same thing to both sides, that's just using logic. No axiom used, right? And we can put parentheses here. We can start with the parentheses like that on that one, because we had 1 plus 1, then we plus a y there. We don't need parentheses over there because we don't have 2, right? Okay, but that gives me, I know from axiom 2 that I can move this parentheses over here, right? So I can rewrite this as 1 plus y is equal to 1 plus y. And that was using axiom 1. Sorry, I'm not writing out how I'm using them since I don't have space. We'll write them out as we use them when we do those proofs up there. But now, what is 1 plus y? 0. So that gives me that 1 plus 0 is equal to 0. But what is 1 plus 0?
It's 1 because of the third.
1 equals, 1 plus 0 is 1. That's using axiom 3. Anything plus 0 is just that thing. So 1 plus 0 is just 1. And 0 equals 0. So I get 1 equals 0. But axiom 10 tells me 1 is not equal to 0.
Okay.
So my assumption that 1 plus 1 equals 1 is false.
Right.
So since this is false, this is false. You with me? So we just barely proved 1 plus 1 is not equal to 0, or is not equal to 1. And we can do a similar thing to prove that 1 plus 1 is not equal to 0. So if 1 plus 1 isn't 0, and 1 plus 1 isn't 1, and 1 plus 1 is a number, we just came up with a new number. This is crazy.
Wow.
And since we have a new number, we got to come up with some new wacky symbol to signify this number. I may start with like an S, and then, I don't know, cut it, weird, backwards S. That's what we'll use for 1 plus 1. That weird, funky symbol. Alright? So now we got a new number, and I know I can take that number and add 1 to it. And we can show that's a different number too. So I'll come up with a weird, funky symbol for that one as well.
Right.
I'm called 3. And now I can define 4, and 5, and 6, and 7, and 8, and 9. And now I don't want to come up with any more new symbols. So I'm just going to do a 1 with a 0 like that. And this one is 9 plus 1. And since we only alternate through 10 different symbols, we use a base 10 system. Right?
I have a question. So when you're defining a new number, do you have to prove that it's not equal to every other number that you know to be in the set R?
It's given, when you come at this with Pino's axioms, this is actually the trivial. Plusing 1, you call it the successor. And it's trivial to show that a successor is never the same as something that came before it. So we're actually doing it the hard way here.
Okay, I see.
But you actually only need to show it once. And it's just one proof to show it for all the integers. Or all the naturals so far. Okay, so we just really showed there's a 0 in there, a 1, a 2, a 3, a 4, ... right? And those are all the numbers that we've shown are in there so far.
Okay.
And that's all we've shown so far. Right? But you know of some other numbers that we haven't talked about yet.
Yeah.
What's another number that you know about that's not in there?
-1.
-1. Oh, we haven't written a -1 in there yet. Do we know that -1's a number?
I mean, I guess.
We don't know it yet, but I'm saying from our regular education, you know
Yes.
-1's a number. So somehow these axioms better tell us -1's in there. And they do.
Axiom 4. Right?
Axiom 4. Axiom 4 tells us that for every number, namely 1, there has to exist some other number, y, such that when you add them together, you get 0. That y is going to be negative 1. And that's how you get negative 1.
Can you prove that?
We'll have a better proof. We'll handle all the negative numbers in one go with the proof.
Okay.
But I want you to see intuitively from the axioms where these are coming from.
Right.
Okay, so I give us all the positive and the negatives. What about fractions? What about something like 1/2?
Axiom 8.
Axiom 8. Perfect. So over here, I know that 3 is a number, right? And axiom 8 tells me for any number that's not 0, is that 0?
Nope.
No, so we're good. For any number that's not 0, there exists some other number, y, such that when you multiply them together, you get 1. And that number we call 1/3. That's our fancy symbol for the number that makes that true. And that's how you get 1/3. Huh?
Can you prove that?
Yes, we'll handle all the multiplicative inverses in one go as well.
Okay.
So negative numbers and multiplicative inverses, we'll handle them all in one go. I just want you to see intuitively where the numbers are coming from. So the axioms, they just told us about 0 and 1, and then these rules imply all the other numbers exist.
Yeah.
And now you have definitions for numbers. What's the definition for 7? Our definition for 7 is 6 plus 1. Well, what's our definition for 6? 5 plus 1. And it goes all the way back to, what's our definition for 2? It's 1 plus 1. What's our definition for 1? It doesn't have a definition. It's given meaning in the axioms. You don't define the terms in your axioms.
Interesting.
You can't define everything. Does it make sense that you can't define everything? What happens if you try to define everything? It's like what happens if I give you, let's pretend you don't know a single word of French. And I give you a French dictionary. You with me? You open that French dictionary, you see a French word, right? And it says, this French word is defined to be, and it gives you a bunch of other French words. So you look at all those other French words, and now you gotta go look all them up. And when you go look up all those other French words, what do you see?
French words.
A lot more French words. And you go look up all those French words, and what do you see?
French words.
More French words. And one of two things is going to happen. Either you've got an infinite dictionary, which goes on forever, introducing more and more and more French words, or eventually it becomes circular. And in trying to define French word A, they said, go look at French word B. And trying to define French word B, they said, go look at French word C. And trying to define French word C, they say, go look at French word A. And you're back where you started. Circular reasoning. We don't allow it in mathematics. So you can't define everything. Axioms are given their meanings. Terms in the axioms are given their meaning, not through definitions, but through the axioms themselves. What are the numbers 0 and 1? They're the two numbers that satisfy these 10 rules. That's what they are. Yeah, but what's their definition? Bad question. You're talking to an ignorant person. It's like asking, what does Uptar smell like? What's Uptar? I was trying to make up a word. I don't know if that's actually something. Some nonsense. They're talking nonsense when they're asking for the definitions of 1 and 0 with the axiom system that we're using. Technically, you can start with set theory and build these axioms.
Right.
For those of you who have had set theory, for those of you that haven't, just stick with what I'm saying here.
What's sweet is you could go from set theory to this.
Yeah, you can go from set theory to any field of mathematics. That's the amazing thing about set theory. But, so these are our 10 axioms that we're going to work with. And we're going to show that if these 10 axioms are true, we won't prove any of them today, unfortunately, we're running out of time. Maybe we'll prove just one to get a feel for it.
Okay.
But move my camera here so that we can see what I wrote there, because I was super ambitious about how far we were going to get today. First thing we're going to prove is that there exists with an explanation point means there exists one and only one.
Okay.
So there exists one and only one 0. Oh, have you guys seen that symbol? That just means in. There exists one and only one 0 in the real numbers. In other words, there isn't some other number. So for example, this number 4. How do I know that this number 4 doesn't act the same way as 0? Maybe it's not the same thing as 0, but maybe x plus 4 is always equal to x as well. Maybe there's some other number that we eventually get that also satisfies the properties that 0 does. First thing we're going to prove is, nope, 0 is the only one. Make sense?
Yeah.
Next thing we're going to prove, well, let's just do that proof just to see one proof. And then I'll just talk out a few of these and then we'll be done. So let's actually do this proof. Prove that there's one and only one zero element in the real numbers. So proof there is one and only one zero element. And when I say zero element, I mean thing that satisfies the axioms that zero satisfies in the real numbers R, in that set. There's only one thing that behaves like zero, and there isn't another one. You with me?
Yeah.
So 1. Let 0 and 0 prime be two zeros. I don't know how I want to say that, because we were using two different symbols. I'll say it this way. Let 0 prime, some new symbol, some eventual number, maybe if you keep going on that, by the time you get to 1654, it starts behaving this way. So let 0 prime be a 0 element. So assume that 0 prime is anything, any number that satisfies the properties that 0 does. Right? And I'm going to show you, anytime you have some random symbol, some random number, 0 prime, that satisfies the axioms that 0 does, you really just grab 0 again. So I'm going to reach into the real numbers, I'm going to pull out a random number, and I'm going to show if it behaves like 0, it actually is 0, every time. No matter what number I grab out, if it behaves like 0, it really is 0. And so 0 is the only thing that behaves like 0. Does that make sense?
Yeah.
Okay. So let 0 prime be a 0 element, something that satisfies this axiom, axiom 3. It's a number such that for all x, if you have a 0 prime, let's just say that explicitly. Let 0 prime in R be an element in R such that for all x, x plus 0 prime is equal to x. You with me? Now I'm going to show that the 0 prime is really 0. It's the only thing that does it. 2. Then 0 prime is equal to 0 prime plus 0. Right? This is using axiom 4. By axiom 4, x plus 0, well, we're kind of using 2 in one go.
Isn't that 3?
Oh, axiom 3. Why was I saying 4 this whole time? Or no, I said... I'm not sure if I was saying it right. Yes, axiom 3. Thank you. Axiom 3. So axiom 3, we just have it written a little bit backwards, but let's make sure we have the right order. We have some symbol plus 0 is equal to 0 is equal to that same thing. So I'll even just write it in the same order so that there's no confusion. So that axiom says that 0 prime plus 0 is equal to 0 prime, right? Observe that, well, you don't really have space there, that 0 prime plus 0 is also equal to 0 plus 0 prime. How do I know that?
Your commutative property?
Commutative property, axiom 1, right?
Okay.
Then 0 prime plus 0 is equal to 0 plus 0 prime is also equal to 0 by assumption. Meaning we said, assume that 0 prime is some number such that when you add something with 0 prime, you just get out that same number. So I know that 0 prime plus 0 is equal to 0 plus 0 prime using axiom 1. And then we said, assume that 0 prime behaves this way, so that you get 0.
Well, you got 0.
So I had 0 prime plus 0 is equal to 0 prime, and I had 0 prime plus 0 is equal to 0. Therefore, 0 is equal to 0 prime is where I'm going with this. So then 0 prime plus 0 is equal to 0 prime, and cords my way. And we showed sugar. And we showed that 0 prime plus 0 is equal to 0. So we showed 0 prime plus 0 is equal to 0 prime, and 0 prime plus 0 is equal to 0. Therefore,
They must be the same.
they're the same number. Therefore, 0 is equal to 0 prime. Or 0 prime is equal to 0. And we're done. That's what we were trying to show. We were trying to show any random number out there that behaves like 0 is actually 0. So 0 is the only number in that whole set that behaves that way. 0 is the one and only thing that satisfies this axiom. No other number does.
Can you do that with 1 as well?
Show that 1 is the only thing that satisfies this axiom?
Do you go about the proof?
It is the exact same to show that for 1. So we can write that so quick. There is one and only one element in R. Let 1 prime in R such that x times 1 prime is equal to x. Then 1 prime times 1 is equal to 1 prime. Observe that 1 prime times 1 is equal to 1 times 1 prime. And that's going to be axiom. Oh, we didn't replace the axiom here.
Axiom 7.
1 prime times 1 is equal to 1 prime. That one's axiom 7. And then 1 prime times 1 is equal to 1 times 1 prime. That's axiom,
1 or
no, 5.
5, yeah.
5. Multiplication is commutative. You can change the order. Then 1 prime times 1 is equal to 1 times 1 prime, which is equal to 1 by assumption. We said, assume that 1 prime is a number such that anything times 1 prime gives you that thing. And so 1 times 1 prime gives you that thing.
Yeah.
Right? By assumption. Then 1 prime times 1 is equal to 1 prime, and 1 prime times 1 is equal to 1. Those were the two things we showed. Therefore, 1 prime is equal to 1. And so we also know there's 1 and only 1. There's 1 and only 1 in R. And we showed that. And it's the same thing. And you see how somehow talking about 0 with plus and talking about 1 with multiplication, there's a lot of similarities there. And for those of you who did a little bit of algebra in discrete math, groups help try and capture some of these similar abstractions. For those of you who didn't, that doesn't have to make sense. That's fine. It's a ways up there. Okay.
So we go over rationals and integers and naturals, but what about irrational numbers?
So that's what I gave you the big warning about. The axioms that we're going to cover do not guarantee the existence of irrational numbers.
Oh, I see.
And so that one you're just going to have to take my word for it. Because proving it is not trivial, and you need to be very comfortable with proofs, and very comfortable with just algebra in general before you start tackling
Will
the
we do it in
incompleteness
this
axiom.
class?
Now, that's the beginning of real analysis course, which is the foundations of calculus.
Oh, I
Real
see.
analysis is proving calculus.
Yeah.
And calculus is just an analysis of the real numbers. That's all you're doing. Calculus is just saying, what do we know about the real numbers? That's calculus.
So in this class, we're only going to do up to the rationals?
No, we'll work with irrationals. You're just going to have to take my word for it that an
Oh.
irrational number is a number.
Okay.
that square root of 2 is a number. And that's irrational. We'll prove it's irrational, but we'll assume that there's such thing as irrational numbers. Because, yeah, the completeness axiom, it's just too hard to work with. You're not comfortable talking about some subset of real numbers having a least upper bound. If it's bounded from above, it has a least upper bound. But that's the assumption. And how that leads to the existence of the irrationals is in no way intuitive. I mean, you end up proving, what's the square root of 2? Take negative infinity to take the set of all numbers x such that x squared is less than 2. And you need to define all these things before you talk about that. But then the least upper bound of this set we define is a number by the least upper bound property, and we call that number the square root of 2.
I see.
But it's a lot of work to get there. Anyways, so we'll call it there. We'll come back and we'll start doing these basic proofs for what we know about the real numbers. So we have these 10 assumptions. We're going to start seeing a bunch of things that those 10 assumptions give us. Like we're going to prove that any number times 0 is actually equal to 0. Wouldn't that be nice to know? Or that a negative times a negative gives you a positive. Wouldn't that be nice to know? Right? That's the really weird one. How is it that if I have negative 4 groups of negative 5 apples, I have 20 apples? Who tricked you into believing that nonsense? So some of these things aren't that intuitive. It's dangerous in this class. Maybe make this note for a second. The hard thing about getting started in a class like this is ignoring things you already know because you've been told it so many times. That's a hard thing about getting started in classes like this. Because you want to just already fall back on things you already know, and the danger in that is it stops you from capturing the misconceptions that you have about those things. And so if you go back and do it thoroughly from the foundations, and you'll try to ignore what you already know and just think about exactly what it gives you, that helps you recapture what it is you can and can't do exactly. And then so hopefully when you see me come to the academy, you know algebra. And you're not trying to do things like this. And make me die inside a little.
I totally didn't do that.
Very common. Or distributing wrong. So many times you guys distribute wrong. So to think carefully about exactly what it is you know, and only draw those conclusions exactly that you can draw. And stop relying so much on just what you got comfortable with, and stop and think about it. And so even though we're going to prove a bunch of things that you're already comfortable with, and you say, oh, that's obvious, the point is to get you thinking carefully about it, and being able to justify how exactly you know that's true. That's the point. It's not because it's so crucial for you to know the proof where negative times a negative is a positive. That's not the crucial part. The crucial part is you're able to think critically about what exactly it is you can assume and what exact conclusions you can draw. That's all of math. If you get that down, you've got math down. I don't care the field. You get really good in one field of math, you're pretty much good in any field of math. That's how it all works. And you get that down in math, now you got science. Just comes for free, almost. Not quite. No, physics is hard. But anyways, we'll call it there, and see you guys next week.